Hi there. In this video, we will look at some examples involving angle pairs. Some terminology is written on the left side of the screen. Let's look at an example. Here we have a diagram, and we want to find the measure of some of the angles. Using the supplementary angles definition on the left, we see that the 67-degree angle and angle 2 are supplementary, which means they add up to 180 degrees. Subtracting 67 from both sides to isolate the measure of angle 2, we get that it's equal to 113 degrees. To find the measure of angle 3, angle 3, we take note that it has a vertical angle of 67 degrees. And from the definition on the left, we know vertical angles are equal. So measure of angle 3 is equal to 67 degrees. Similarly, angle 2 and angle 4 are vertical angles, so they are equal to each other. So measure 4 is equal to 113 degrees. Let's take a look at another example. First, we need to solve for x by noticing that angle 1 is supplementary to the angle 2. Which means they add up to 180 degrees. So we can use that to create an equation and solve for x with some algebra. Once we isolate x, we get that x is equal to 8. Now we can use that to find the values of angle 1 and angle 2. Plugging in 8 for x gives us that measure angle 1 is 75 degrees. Also note that angle 1 and angle 3 are vertical angles, so they are equal. So measure of angle 3 is also equal to 75 degrees. To find out what angle 2 is, we plug 8 into the expression 14x minus 3. evaluating it, we get angle 2 is equal to 105 degrees. Angle 4 and angle 2 are also vertical angles, so they are equal. So angle 4 is also 105 degrees. Another example. First, we notice that angle 1 and angle 3 are vertical angles, so they are equal. So setting their expressions equal to each other, we can solve for x. Now we just use a bit of algebra to isolate the variable x. We end up with x equals 3. Now we can use that to find out the measure of angle 1 and angle 3 are. Plugging in 3 for x into 7x plus 7, we get that angle 1 is 28 degrees. Since measure of 1 and measure of angle 3 are vertical angles, they are equal, so measure of angle 3 is also 28 degrees. Now let's find the measure of angle 2. We know that measure of 1 and measure of 2 are supplementary angles, so we can write an equation for that. Then isolate measure of 2 to get that it is 152 degrees. And since measure of angle 2 and measure of angle 4 are vertical angles, they equal each other. So measure of angle 4 is also 152 degrees. Now we will look at some examples involving the distance formula. But first, let's review solving quadratic equations by factoring and using the square root property real quick. For example A, we will do by factoring. We can factor this quickly by looking at factors of negative 14 that add up to negative 5, which are the middle term's coefficient. In this example, we can factor it as y minus 7 times y plus 2. Then we set the 2 equal to 0 and solve each equation. We end up with x equals 7 and x equals negative 2. For example B, we'll use a square root property. The square root property says if you have something squared on one side that is equal to a number on the other side, that something will be equal to the plus or minus of the square root of the number on the other side. We will show this in this example. First, let's factor the left side by looking at factors of the constant that add up to the middle term's coefficient. Notice this is a perfect square, meaning we now have something squared on the left side and a number on the right side of this equation. This means that the something on the left side, which is x plus 4 in this case, will be equal to the plus or minus square root of 18. Then we isolate the x by subtracting 4 from both sides to get our answers of negative 4 plus or minus the square root of 18. Now let's do a couple of examples involving the distance formula, which is on the left side of the page. Using the formula, let's label the 2 points as the formula describes. Now we can just plug in the values into the distance formula and evaluate. Don't forget about order of operations here. We need to simplify the parentheses, then exponents in the radical, then simplify inside the radical. Now another example. Here we are looking for the x-coordinate that satisfies the conditions we are given. So let's label the given points so we can plug them in the distance formula and see what to do next. After labeling our known values, we can plug them into the distance formula. Now we use order of operations to simplify as much as possible. Distributing and simplifying inside the radical here. More simplifying here by combining like terms. We don't want a square root in our equation if we can help it, so let's clear them by squaring both sides. Now let's get 0 onto one side and see if we can factor the polynomial. If factors of 20 add up to negative 12, it is factorable, and negative 10 and negative 2 are those factors. So we get two solutions of x equals 10 and x equals 2. We do need to check our answers to see if they both make sense or not. Let's plug 10 first. Simplifying, we see that it checks out, so x equals 10 is definitely a solution. Now plug in 2. Simplifying, we see that this also checks out. Now we will look at a few examples that are in the homework involving transformations. We will also use Desmos to help us out as well. For question 2, we want to reflect a point over the x-axis, and this is done by using the opposite y value of the original point. We can verify this using Desmos. Let's enter the original point, negative 2, 3, Then enter -2, -3 as mentioned earlier. We can also look at the definition of reflection above to see what reflection means. Here I am just inputting what we stated earlier, that the reflected point should be -2, -3. This question also asks to reflect it about the y-axis as well, which you can see that would just use the opposite x value of the original point. Here's the point -2, -3, which just shows the point reflected about the x-axis. Now let's input the point reflected about y-axis. Again, which is just using opposite value of x, so 2, 3 instead of -2, 3. Looks good, right? Now let's look at an example using a shape on the rectangular coordinate system. Flipping it over the x-axis, remember it's using the opposite y value of the original point. So here, if we look at each of the vertices on the square, then flip it over the x-axis, we will have done it. Whoops, let's redo this so we don't have a diagonal line. There we go, and this is reflected over the x-axis. Now we do a similar process to flip the shape over the y-axis. Remember, this is done using the opposite x value of the original point. Again, this is made easier by using the vertices of the square. Looks good. Now we'll look at an example where we rotate a point by 90 degrees counterclockwise. The way I look at it is by trying to envision part of the x-axis moving down to the y-axis and the point follows. So instead of being -5, 3, it now will be at 3, -5 after rotating it. Similarly, when rotating it 90 degrees clockwise, moving the x-axis up to the y-axis, we get the point -3, 5. Just verifying real quick here. Now let's rotate a shape. Similar process as before, looking at the vertices and rotating them counterclockwise or clockwise. First, we do it counterclockwise. Again, I think of it as rotating the x-axis down to the y-axis, and the shape follows. Now rotating it 90 degrees clockwise, same process, move each of the vertices, and done. Here is an example where we use a translation to basically just move a shape from one spot to another spot on the graph. Again, use the vertices to make things easier, and just subtract 1 from the x value and add 2 to the y value in this case.